The Big Bang Theory is widely accepted as the most plausible explanation for the beginnings of the universe. This hypothesis states that 13.8 billion years ago, the universe was a singularity, an impossibly hot and dense point. Everything that we see now, including stars, planets, and living things like humans, was created as a result of this singularity's quick expansion. For such a significant event, the term Big Bang may seem fanciful, but it accurately conveys the idea of a massive explosion from which the universe formed. After stuff dispersed and cooled over billions of years, planetary systems, stars, and galaxies were finally formed. The Big Bang Theory has encountered difficulties over time due to the emergence of fresh evidence and observations, despite its broad acceptance. The James Webb Space Telescope, JWST, was launched by NASA with the expectation that its unparalleled capabilities would add to the body of evidence proving the Big Bang Theory. But after only a year in orbit, the telescope started taking pictures that contradicted what was known at the time. These pictures showed galaxies so old that they might change how we think about the origins of the universe. Astronomer Rohan Naidu's astounding observations while examining early telescope photos in July 2022 set the stage for the JWST's historic discoveries. When Naidu and his colleagues discovered a galaxy they had never seen before, they named it Glass C13. This galaxy is the oldest galaxy ever observed, having formed only 300 million years after the Big Bang. Glass C13's findings shocked the scientific community, surpassing even the most hopeful predictions for the JWST's capabilities and proving that it might completely transform our knowledge of the early cosmos. The JWST was built to investigate the cosmic dawn, the period immediately following the Big Bang when the first stars and galaxies started to form, and it is situated millions of kilometers away from Earth's interference. With its enormous segmented mirror and extremely sensitive equipment, the telescope sought to reveal information about this little-studied era of cosmic history. But the telescope's first results were surprising. Rather than discovering dim, far-off galaxies as predicted, astronomers found many galaxies with unexpected features, such as brightness, size, and age. The relevance of current models and ideas was called into doubt by the abundance of mature early galaxies. Scientists stepped up their efforts to comprehend the significance of the JWST's findings in reaction to these surprising discoveries. They conducted more observations and studies to better understand the beginnings of the universe and solve its mysteries. Researchers continue to discover surprising events and fresh insights as they use the JWST to probe farther into the cosmos. Every new finding advances our grasp of the universe's workings and our place in it. Deep questions concerning the nature of the universe and our comprehension of its origins have been brought up by the JWST's discoveries. These findings raise the potential that the cosmos is significantly more complicated and enigmatic than previously thought, even though they may be explained with conventional cosmological models with additional research. The first chapters of cosmic history could be rewritten by the early discoveries from JWST. These chapters contain consequences for our existence in the Milky Way galaxy in addition to distant galaxies and epochs. The spirit of scientific exploration is perfectly encapsulated by Mark McCarran, a senior consultant for research and exploration at the European Space Agency, creating machines that test rather than validate pre-existing assumptions. The revolutionary discoveries made by the JWST began in 1985 at the Space Telescope Science Institute. Visionary leaders like Ricardo Giacone recognized the need to make plans for the future, even if the Hubble Space Telescope was still years away from launch. The next-generation space telescope, eventually known as JWST, was conceived as a result of conversations about what would follow Hubble, according to Jellingworth, who was Sky's deputy director at the time. The JWST was designed to observe in the infrared spectrum in order to get around Hubble's constraints. By catching light from galaxies that had been stretched into the infrared by the universe's expansion, this capability would enable it to look farther into the cosmos. The choice to concentrate on studying early galaxies became the main scientific objective for JWST, underscoring the telescope's potential to transform our knowledge of cosmic dawn. The groundbreaking Hubble Deep Field observations in 1995 highlighted the necessity for a telescope such as JWST. Notwithstanding early doubts, the prolonged study turned up hundreds of galaxies that date back billions of years in the universe's history. The foundation for JWST's next observations was laid by this finding, which revealed the early universe's richness and complexity. Finally, on Christmas Day 2021, JWST opened after more than 20 years of development and an estimated $10 billion. A new era in astronomical exploration began when it reached its deep space target. With high-impact activities designed to solve the mysteries of the early universe, JWST launched Cycle 1, its first year of science observations, in July 2022. The hunt for galaxies in the early universe was the focus of two of these programs, the GRISM Lens Amplified Survey from Space and the Cosmic Evolution Early Release Science Survey. JWST observations challenged preconceived notions about the galaxy formation timeframe by revealing incredibly distant galaxies right away, in contrast to initial expectations. Astronomers are excited and speculative about these early discoveries, which raise the prospect of much more significant discoveries down the road. With the potential to solve cosmic riddles and transform our knowledge of the universe's beginnings, the JWST is a monument to human ingenuity and curiosity. Our view of the early cosmos has undergone a significant reevaluation as a result of the JWST discoveries. The unexpected brightness and size of galaxies seen at very far distances that defy accepted cosmological models are a major component of these discoveries. A 2009 upgrade that improved the telescope's infrared capabilities has allowed JWST to push the limits of observation, giving scientists the ability to see farther back in time and deeper into space than ever before. Previously, it was believed that galaxy formation began at a critical redshift of 11, which corresponds to a cosmic age of roughly 400 million years after the Big Bang. But early JWST images, especially those from the GRISM Lens Amplified Survey from Space, showed galaxies like GLASS Z13 with a redshift of 13, suggesting that they are closer to the Big Bang by about 70 million years. Due to their unexpected brightness and size, these galaxies called into question accepted notions on the chronology and processes of galaxy formation. The standard cosmological model, lambda cold dark matter, lambda CDM, which incorporates scientists' best estimates for the properties of dark energy and dark matter that collectively govern the emergence of large-scale cosmic structures, does not account for the rapid emergence of galaxies with estimated redshifts as high as 20 just 180 million years after the Big Bang. The sluggish action of matter over billions of years is necessary for the development of huge galaxies, which should have taken far longer, according to lambda CDM. It is crucial to take into account the early phases of the universe's evolution in order to comprehend the consequences of these discoveries. The universe was a dense, boiling soup of primordial particles in the first second following the Big Bang. The first elements of light formed during the next several minutes as the universe cooled and expanded. Conditions were favorable for the first stars to form some 100 million years after the Big Bang. Without the heavier components seen in stars today, these early stars were bigger and brighter. Over billions of years, they merged to form protogalaxies, which in turn gave rise to larger galaxies. By displaying galaxies that seem larger and more developed than anticipated during such early cosmic epochs, JWST's findings cast doubt on this story. The lack of many tiny protogalactic shards raises the possibility that galaxy formation was a more complicated and quick process than previously believed. Even though dust obscuration may make some galaxies appear larger, further studies using tools like Chile's Atacama Large Millimeter Array have verified that there isn't always a lot of dust present, proving that these galaxies are in fact quite massive and brilliant. These discoveries have significant ramifications for our comprehension of the early history of the cosmos and the basic ideas of cosmology. They imply that in order to explain the surprising findings of JWST, the conventional cosmological model might need to be modified. Uncovering the secrets of the early universe and improving our comprehension of cosmic evolution will require further investigation and study. According to Bohn Kulian, the findings from JWST may have a big impact on how we think about gravity and dark matter. He brought up the contentious theory known as modified Newtonian dynamics, MOND, which contends that large-scale gravity fluctuations could account for the properties previously ascribed to dark matter. Such a notion may be supported by JWST findings, according to Bohn Kulian. Milos, a supporter of MOND, pointed out that a lot of its predictions have come true, indicating that it might be a good substitute for dark matter. But not every scientist agrees that MOND is a good idea. Skepticism was voiced by Cartage, an astronomer at the Rochester Institute of Technology, who said that MOND has not yet produced satisfying results in numerous testing. The absence of dust could also be the reason for the early galaxy's surprising brightness. Early universe galaxies might have had little to no dust, which would explain their unusual brightness. In addition to potentially explaining why ALMA had trouble detecting glass C13, this could make it more difficult to determine the galaxy's actual masses. Ferrara suggested that the brightness of early galaxies might have resulted from the expulsion of dust during the early stages of galaxy formation. Mason and her colleagues hypothesized that JWST might only be monitoring the early universe's brightest newborn galaxies, which would be simpler to find. Theoretical astrophysicist Spell suggested that higher gas pressures and temperatures in the early cosmos made high-mass star creation extremely efficient. He hypothesized that magnetic fields may have formed sooner than previously believed, propelling material to begin the formation of stars. The enthusiasm and urgency surrounding the telescope's discoveries are reflected in the quick publication of scientific publications after JWST's first observations. Astronomers chose to publish their findings on AR-14, a website that allows scientific articles to be posted and instantly seen by the scientific community, rather than going through the conventional peer review procedure. A new type of peer review known as Science by AR-14 is developing in almost real time on social media sites like Twitter as a result of the quick spread of scientific results after JWST's initial observations. Scientists were able to have heated and unexpected conversations as a result of this phenomena. Although this strategy made it easier to quickly publicize and discuss the findings, several people were worried about moving too quickly. Traditional peer-reviewed articles are the highest standard for scientific confirmation, according to Klaus Pont, JWST project scientist at SDSCI. For example, JWST's early calibration problems might have impacted some results, leading to warnings. The necessity for rigorous investigation was highlighted by Nathan Adams of the University of Manchester and his colleagues' discovery of striking variations in redshift readings for certain galaxies. Even with possible calibration problems, astronomers are nevertheless hopeful about the importance of JWST's findings. The sheer quantity of high redshift galaxies found raises the possibility that the early universe differs from what was first thought, even though it is doubtful that all of the results will be disproved. Astronomers are rushing to use JWST to perform follow-up observations in order to verify and examine high redshift galaxy candidates in light of these findings. In order to further study these galaxies, several suggestions are being reviewed for more JWST observing time, according to Nancy Levinson, temporary director at SDSCI. By scanning a larger region of the sky for longer periods of time, projects like Cosmos Web, which is headed by J. Harley Cartage, hope to greatly expand the known population of early galaxies. Astronomers are also looking for ways to find evidence of the initial protogalaxies, perhaps by utilizing brilliant supernovae and the deaths of supersized early stars as markers. The thrill of JWST's discoveries heralds a new age in astronomy, one in which scientists will collaborate and communicate more quickly. The possibility of reassessing our knowledge of the early cosmos has energized scholars despite uncertainty. Confirming even a small number of these high redshift galaxies would be incredible, as Rohan Naidu so eloquently stated, proving that we are not being misled in our search for the universe's mysteries.